Every light bulb, humming refrigerator, and spinning industrial motor across North America is singing the exact same note. It's a low, constant B-flat. Every watt consumed across the network must be generated in the exact same millisecond it is used. The grid is a live delivery system with no storage capacity. Because demand and production are linked instantly, every action has a physical consequence. When you push down the lever on your kitchen toaster, a massive nuclear turbine 3 states away actually feels a tiny bit of mechanical drag. To handle that shifting demand, thousands of massive turbines from Canada to Florida spin in a synchronized choir. They are locked together by a 60 cycle per second vibration, or 60 hertz. We call it the grid's heartbeat. These machines are physically locked into a single, rigid rotation across thousands of miles. If that pulse deviates by even a fraction of a percent, the entire continent goes dark in seconds. This synchronization is a requirement of alternating current, or AC electricity. Unlike a battery, where electrons flow in one continuous direction, AC electricity plays a game of tug-of-war. The electrons move forward, then backward, then forward again. One full electrical cycle, forward and back, is exactly 1 hertz. In North America, that cycle repeats 60 times every single second. Because the electrical wave and the physical machines are linked, the frequency dictates the speed of the generators. To maintain a 60 Hz pulse, a standard 4-pole generator must spin at exactly 1800 RPM, not 1801, not 1799. This constraint is a legacy of Nikola Tesla. He found that 60 Hz was the most efficient frequency for induction motors and prevented arc lamps from flickering. A practical engineering choice made over a century ago became the inescapable physical law governing a continent-sized machine. Keeping thousands of generators at that exact speed requires constant balancing. Imagine a fleet of tandem bicycles all welded together. If one person pedals harder, the whole line speeds up. If one person stops, they are dragged along by the rest. Grid operators track this balance in real time. The green center represents a perfect 60 Hz. When millions of people turn on their air conditioning units at once, the system feels that added drag, dropping the pulse to 59.9 Hz. If those units are turned off suddenly, the resistance vanishes. The generators speed up, and the frequency pushes towards 60.1 Hz. Plant operators must adjust fuel flows continuously to counter these swings. If a single power plant tries pushing electricity out of phase, meaning its wave peaks while the grid's wave troughs, the magnetic forces act like a crowbar thrown into a spinning engine. The generator would literally rip itself off its concrete moorings. Preventing that destruction requires absolute millisecond-to-millisecond synchronization across thousands of miles. The grid does have defense mechanisms. If the frequency drops to 59.5 Hz, turbines begin to vibrate violently. To save them from exploding, computers initiate load shedding, forcibly cutting power to entire neighborhoods to lighten the drag on the generators. But a single physical event can sometimes outpace these defenses. A sagging power line touching a tree branch in Ohio is enough to create a massive short circuit. This happened in 2003. As safety systems tripped one heavily loaded line, the electricity instantly rerouted to others, overloading them. Power plants fell out of sync and disconnected like dominoes, leaving 50 million people in the dark. Even at this massive scale, tying every machine to a perfect 60 Hz pulse makes the system susceptible to rapid, cascading collapse. Historically, the grid relied on physics to buffer these shocks. Massive steel rotors spinning inside coal and nuclear plants have tremendous momentum. They act as physical shock absorbers, providing natural inertia that keeps the frequency stable during sudden demand spikes. Look at a modern wind turbine. As we transition toward renewable energy, we are replacing heavy, synchronous machines with a different technology. Solar panels and wind turbines don't inherently spin at 1800 RPM. They use digital inverters to match the grid's frequency. Because they lack heavy spinning iron, they provide no physical inertia to the system. Retiring those massive steel rotors strips the grid of its natural shock absorbers. The physical heart of the network is shrinking, making that 60 Hz pulse more vulnerable to skipping a beat. Next time you plug in your phone, remember that you're tapping into a single continent-wide circuit spinning in unison at 60 cycles per second. Just hope the heartbeat stays steady.